Hello everyone, welcome back to the session. So today's class what we are going to do is we are going to solve some numericals from thermodynamics. Alright, so with this note let's begin. My name is Mohana, I'm a physics educator here at Unacademy. I'm also a plus verified educator and I have my master's degree in physics, so you can follow me through this telegram channel, and this is the common ICSE and ICSE board telegram channel. You can follow this channel also. Right now, if you're taking the plus subscription, we have up to 23% off. So if you're taking the subscription, now might be the best time. So with that, let's begin. Okay. And first question, what we are going to do is we are going to solve one question. Okay, based on work done during a cyclic process. Okay. Let's say we have a cyclic process. Now let's say this is given in terms of volume, right? And this is your PV graph. Okay. And let's say this particular volume over here, let's say this corresponds to 200 centimeter cube. Okay, and let's say this particular volume corresponds to somewhere around if this is 200 means let's go with this with 400 centimeter cube. Okay, similarly let's look at the pressure. Let's say this point over here, let's say the pressure is somewhere around 200 kilopascals. Okay, at the same time somewhere around here let's say the pressure is around 300 kilopascals, right? So a thermodynamical system is taken through a cyclic process. Okay, and let's say the cyclic process it goes through is basically P, Q, R, S and back to P, which means it goes from P to Q, then Q to R, then R to S, right? Then we have S to P. This is the system in which it's going. What we want to do is, we want to find what is the work done. What is the work done on the system? Okay, what is the work done on the system? That's what we want to go. We want to actually find. Hi Nitin, right? Very simple. How would you find for a cyclic process? What is the work done by the system? Very simple. Over here, you just have to find area of this curve over here. All we have to do is find what is the area of this curve. This gives you work done during this particular process. Now, if you know the answers, you can give it in the chat box. So, how do we find the area over here? Very simple. Okay. This is basically work done. What is work done in this case? Let's say this is work done. Let me do this here. Work done in this case is nothing but area, right? Area. Okay. Area of the loop. Now, there is two things we have to, okay, area of the loop, PQ, RS, P. Now, there is two things we have to, you have to check over here. One is, what does the sentence read over here? It says, work done on the system. Okay, work done on the system. Work done on the system means, then area under this graph is going to be a negative value. How do we also know that? See, the process over here is in anti-clockwise direction. Look at the direction in which this process is happening. So, okay, this is happening actually in an anti-clockwise direction. There itself is a clue that the work done in this case is negative. Why? Work done on the system is negative. Work done by the system is actually a positive value. So, this is going to be a negative value. We could have easily gone with this if only we did not have the option 0 over here. But because we have 0, we have to check over here, which is going to be the answer. So, how do we find the work done in this case? Very simple. This particular work done over here is going to be, what is the area over here? Area over here, this is a rectangle, right? So, we can check length into breadth, right? So, what is the length over here? How do we give this particular length? Okay, length into breadth. Let's directly substitute over here. On one end, what we have? The difference in volume. What is the difference in volume? On one end, we have 400, okay? Another hand, we have 200. The unit is in centimeter cube. Okay. Into what about this side? We have, this is nothing but again difference between pressure, that is this side length. This side length will be this value minus this value, right? This is this side length. So because if you find out what is this length and what is this length, that will multiply them, you will get the area of the rectangle. So what about this side length over here? This is going to be nothing but 300 minus 200. Okay, now what is the value? Kilopascal. What do we need the unit as? Joules. So this is why you have to be very careful. You have to convert all the units over here. So this will be minus 200. Okay, into, very simple, what is 1 centimeter? 1 centimeter in terms of meters, because we want to express this in terms of joules. 1 centimeter to meter is, 1 meter is into 10 to the power of minus 2 meters. We have centimeter cube. So this whole cube, that is nothing but this whole cube. So 1 centimeter cube is 10 to the power of minus 6 meter cube. So this is 400 minus 200 is 200 into 10 to the power of minus 6 meter cube into, okay, this is one term we have. Another term we have is what? This value, 300 minus 200, that is 100. Kilo is 10 to the power of minus, right, 10 to the power of plus 3, right, into Pascal. How do we express Pascals? We can write Pascal, okay, Pascal actually in terms of Newton meter, very simple, okay. This we can express in terms of Newton meter, okay, Newton per meter over here, right. So from here what will we end up getting? Okay, Newton per meter square, that is Pascal, alright, because kilopascal, Pascal we are talking about pressure is nothing but force per area, so pressure is Newton per meter square, okay, very simple. I'm sorry, just a second, okay, from here just substitute, solve for this and substitute, you will get the answer over here, very simple, okay. So here you will get actually 2, right, into 10 to the power of, these are 2 zeros here, 2 zeros here, we can take it as 4, into 10 to the power of 3, into 10 to the power of minus 6. What about the units? We have Newton, meter square and meter square, from this if you cancel you get Newton meter. So this basically gives us what? This basically gives us, this is 10 to the power of 7 minus 6. So this is 2 into 10, okay, 10 to the power of 1 we will get. Newton meter is nothing but force into displacement, that is work done, that is nothing but joules, that's the unit of joules, right, very simple. So from here what we get, this is a negative sign over here, so this is nothing but 20 joules, very simple, 20 joules is the answer. Okay, this is work done, this is the equation with respect, this is one numerical with respect to work done during a cyclic process. Okay, now let's do one more, we'll do one more numerical based on Mayer's formula. So what I will do is, I will solve one numerical and you can solve another one. Okay, now if you look at Mayer's formula, what is Mayer's formula? How do we define Mayer's formula? It is given as, what is the molar specific heat? Okay, molar specific heat of a gas at ideal pressure minus, at constant pressure, minus molar specific gas at constant volume. This will be equal to R, which is nothing but the universal gas constant. Right. Now let's see what is the question asked over here. Now the difference between two specific heats of gases are given over here. Difference between the two specific heat of gas is given, and the ratio of the specific heat of gas is given as 2:3. Sorry, 3.2. Now find the specific heat. So they are asking us to find the two specific heat. They have given, let's write what they have given. What is the first term they have given over here? That is, they have given us what is the difference between the two specific heats of gases. So how do we write that sentence first? Very simple, that we can write as, right, difference between the gases, right. So that is nothing but, here it will be, the difference is, let's say this is Cp minus Cv, that is, this is what is given, the first sentence. This is given as 8000 joules per kilogram per Kelvin. You should be very careful with the units, okay. Now what else is given? What is the next sentence that is said over here? The next sentence we can see over here is, okay, the ratio of specific heat is 3.2. The ratio of the two specific heat is 3.2, meaning, okay, if we take a ratio between, okay, between Cp by Cv, then that ratio is 3.2. These are the two questions given. What are they asking us to find? They are asking us to find what is Cp and what is Cv. Right, very simple. If we know this, if we know these two quantities, what can we derive from here? From here we can write Cp is nothing but 3.2 into Cv. So can we substitute that over here? Instead of Cp we can substitute 3.2 Cv. So this is 3.2 Cv, right, minus Cv, right, we are substituting in this equation. This is equal to 8000. Very simple, okay. Now from here this will be 2.2 Cv, right, 2.2 Cv, this is 1 Cv over here, right, this will be 2.2 Cv, which is equal to 8000. So what is Cv? So very simple, Cv will be 8000 divided by 2, 2.2, right. So 8000 divided by 2 is somewhere around 4000. So 8000 divided by 2.2 will be a little less than that, somewhere around 3636. I'll stop with one decimal point. Okay, 0.4. Okay, so one value we found over here. We found what is CV. CV is 3636.4, okay, joules per kilogram per Kelvin. Okay, we found CV. Can we find CP from here? Very simple, right? We can find CP. What will be CP over here? CP will be, right, this particular value 8000 minus 8000, right? 8000 plus CV. Plus CV is what? CV is nothing but 3636.4. So CP over here will be nothing but this value plus 8000, right? That gives you somewhere around, somewhere around 11,636, right? 0.4, right? I'll stop with this, 0.4 joules kilogram per Kelvin. Okay, these are the two answers. Very simple one. Okay, now let's do the next question over here. This one I did. Now you can try doing this question over here. This particular question over here says, calculate the specific heat at constant volume of a gas given the specific heat of a constant pressure is 8.62 calorie per mole per Kelvin, and R value is also given. Okay, the universal gas constant value is also given. Okay, they are asking us to find what is the specific heat at constant volume for a gas. Okay, specific heat at constant pressure is given. Okay, very simple process over here. So what are the two quantities given over here? Okay, let's first write down what is given. Constant, given the specific heat at constant pressure, which means what is the quantity that is given for us? The quantity that is given for us is specific heat at constant pressure. Specific heat at constant pressure, what is this value? This is 6.85, okay, calorie, right, calorie per mole, right, per Kelvin. Very simple. Right, now here R value is given. Okay, compare R value and see. R value is 8.36, right, joule mole per Kelvin. What do they want us to find? Specific heat of constant volume. CV they want us to find. What is the formula? That is, formula is CP minus CV is equal to R. Now comes the conversion fraction. Hello Hafsa, the conversion factor over here. See, this is the unit of work done, right, in SI system of unit, but this is the unit of heat. So we have to make use of the conversion factor, that is J over here. So other units are same, mole is same, kilograms are same, but okay, hello Hamdan, okay, and this particular ratio, if you see, we cannot take this ratio because one is in CJ system, one is the unit of heat. Okay, one is in SI unit, another is in unit of heat again in CJ system. So we have to convert these two particular quantity, which means we have to make use of the conversion factor J over here. Okay, now let's substitute in this and see, we will get the value. What do we want to find? We want to find CV. CV will be nothing but CP, right? CV will be nothing but, in this case, it will be, in this case, CV will be nothing but CP minus R by J. Right, so what is CV? What is CP over here? CP over here is 6.85, right? CP is 6.85 minus R we are dividing by J. Why? Because we are converting from joules to calorie. Okay, because the answer over here is asked for us to be given in calories. 6.85 divided by R is 8.36. Alright, so here we will end up having, 6.85 divided by 8.36 divided by 4.18. Just divide by 4.18. Why we are dividing? We are converting from joules to calorie. Very simple. Okay, so we are dividing. If you want to convert from joules to calorie, divide by 4.18. Okay, so if you solve for this particular quantity, now the unit, all of the unit becomes calorie mole per Kelvin. Okay, so if you solve for all of this, we will get this particular CV value to be somewhere around, approximate value, okay, approximately close to 4.7 something. Okay, the unit will be in calorie mole per Kelvin. So this is an approximate value, not an actual value. Okay, approximately close to 4.7. Yes, Hamdan, I remember. Alright, okay, and with this is the second question. Now, Let's try some more numericals. Now let's try from first law of thermodynamics. Okay, now 8 moles of oxygen are heated at constant volume from 20 degrees Celsius to 30 degrees Celsius. What will be the change in internal energy of the gas? Okay, the gram molecular specific heat of oxygen at constant pressure is given. That is Cp is given. Okay, universal gas constant is also given. Okay, now what is the change in internal energy? Now this is the question that connects basically from first law. You have to use first law of thermodynamics. So if you see what is the first law of thermodynamics, the first law of thermodynamics states the heat supplied to the system, okay, is used as two parts. One is to increase the internal energy and also some amount of work is done. What are they asking us to say? What is du? They are asking us to find du. Du over here is nothing but, okay, actually this is what is the small amount of work done also. Okay, so du over here is nothing but in this case q minus dw. Very simple. We want to find du. Okay, now very simple. What are the quantities we have over here? Alright, some quantities that we know over here. Let's see. The Cp is given. Cp for this case is given, for this oxygen is given as 8 calorie mole, right? 8 calorie mole per degree Celsius. This is given. Okay, now make sure all of these units are actually in CJ system. So go with it. Okay, conversion, always when you're solving any numericals from thermodynamics, make sure to go through these units. Okay, conversion factors are always to be included for. Okay, now look at the R value over here. What is the R value from here? R is nothing but 8.36 joule mole, right, per degree Celsius. You have to convert. We want the answer in calories, so we have to convert joules to calories. So if you want to convert from joules to calorie, what will you do? You will divide this particular quantity by 4.18. Then you will get whatever answer you are getting. If you divide these two, you will actually get 2. So this is nothing but 2 calorie mole, okay, per degree Celsius. That's it. Okay, now one thing we know over here is, okay, we know the Mayer's formula. Okay, now we know this R is also 2 calorie mole per degree Celsius. We know from Mayer's formula that Cp minus Cv, the difference between the molar specific heat of at constant pressure and constant volume, is equal to the gas constant. We know Cp, we know R. So we can find Cv. Cv will be what? Cp minus R. What is Cp minus R? Okay, 8 minus 2, right? 8 minus 2, that is nothing but 6 calorie mole, right, per mole per degree Celsius. Very simple. Okay, now what we want to do? Let's go to the next part of the question. Alright, so one thing we want to find is we have to find this heat factor over here, right? What is the heat gained by this 5 moles of oxygen when it is heated from 20 degrees Celsius to 30 degrees Celsius? What is the heat gained? How would you write that? Very simple. The specific, with respect to specific heat formula, heat gained will be what? What is the number of moles, okay, into heat gain, this particular oxygen, right? 8 moles of oxygen is heated with respect to constant volume. Okay, specific heat at constant volume. You have to use specific heat at constant volume over here. Okay, into temperature. The actual formula is the heat supplied is what is the mass times the mass times the specific heat into temperature difference. What is the change in temperature? But here we are using in terms of, we are defining in terms of molar specific heat. So how many moles of oxygen was used? 8 moles, right? This is given in the question. How many moles of oxygen is used? 8 moles of oxygen, right? 8 moles of oxygens are heated. Okay, now at what? At constant volume. So what is that volume constant? That is the specific heat of specific heat at constant volume. We found the Cv to be what? 6, right? Into what is the temperature difference? What is the temperature difference? Temperature difference is from 20 degrees it's heated to 30 degrees. Temperature difference will be what is the final temperature minus initial temperature. So 30 degrees minus 20 degree, right? Temperature difference will be basically 30 minus 20. So this gives us what? Okay, very simple, right? This is what? 8 times 6, right? So this gives us 8 times 6 is 48. 8 times 6 is 48. This difference is 10. So this gives us 480. This is heat. So many calories. Heat, so we are representing this in terms of calories. Okay, now what is one more concept we know? The entire 8 moles of gas are heated at constant volume. What is work done? Work done, if you want to express, this work done can be expressed as, okay, pressure into the change in volume. Is there any change in volume? No, because the volume is constant, because that means pressure is 0. So what will be the total? What will be the change in internal energy? So change in internal energy will be nothing but what is the heat, right? What is the heat supplied to the system? That is nothing but 480 Kelvin. That is 480 Kelvin minus work done. Work done by the system is 0. So this gives us just 480 Kelvin. So this is your answer. Alright, okay, great. Now let's move ahead. Okay, next question is very simple. A tire pumped at a pressure of 3.375 atmosphere and at 27 degrees Celsius suddenly bursts. Okay, we want to calculate the temperature of the escaping air. Gamma is given as 1.5. This constant is given as 1.5. How do we do this particular question? Okay, how would we do this particular question? Okay, now very simple. Okay, now what do we know? We know pressure is given, temperature is given. So in this case, okay, this is an expansion, right? Thank you for that temperature, temperature Hamdan, right, over here. So it is very simple. Okay, so if the gas is expanding, in this case, this is an adiabatic expansion. This is basically an adiabatic expansion, right? A tire pumped to a pressure of 3.375 atmosphere and at 27 degrees Celsius, it suddenly bursts, right? So calculate the temperature of the escaping air. This is basically an adiabatic expansion, right? The air expands adiabatically. For an adiabatic expansion, how do we give the pressure, right? How do we give the equation for, especially for pressure, equation that connects pressure and temperature, right? So in this case, the equation that connects pressure and temperature will be nothing but, okay, this is nothing but, this is, let's say, initially the system had a particular pressure, right? Then the pressure actually changed. So this we can take it as P1 divided by T1 to the power P1, right? P1 to the power gamma minus 1, where gamma is nothing but Cp divided by Cv. Okay, specific heat ratios between the two specific heat. Okay, very simple. So here this will be P1, okay, temperature wise, equation for adiabatic process if you are taking, okay, we can take P1 V1, alright, P1 V1 into T1, right, gamma, this is equal to a constant value. Similarly, if you take for the next process, because initially it had a pressure, after the tire bursts, the pressure changes, temperature changes. So from there we can say P2 minus 1 divided by T2 gamma, this is equal to a constant. Both are equal to a constant. So we can equate these two equations. Okay, we can equate these two equations. This will be P2 gamma minus 1 divided by T2 gamma. Okay, so from here, if I take a ratio between T1 divided by T2, right? Let me cross multiply. This goes to the other side. Okay, this will be equal to what? This has gone to the other side. This will be P1 gamma minus 1, right, divided by P2 gamma minus 1. So what I am going to do is I am going to take these two constants the same. That is, I am going to take T1 by T2, the whole gamma. This is equal to P1 by P2, the whole power of gamma minus 1. Okay, let me actually substitute for this particular temperature. Okay, now temperature, initial temperature T1 over here is given as what? 27 degrees Celsius. Okay, T1 is given as 27 degrees Celsius, right? Convert it. You can substitute. Let's try converting it into Kelvin, absolute temperature, because T over here is in terms of absolute temperature. Okay, so 27 degrees Celsius is what in terms of absolute temperature. Thank you for that, Hamdan. That is 27 plus, okay, 277, right? You will get somewhere around 300 Kelvin. This is T1. We want to find what is T2. That's the question that is asked. We want to find what is T2, right? Okay, now, okay, after you find it, again convert it back to Celsius again. Okay, so again over here, from here, what we know T1. What about pressure? Okay, see, atmospheric pressure is around 1. Okay, as soon as the gas escapes from the tire, atmospheric pressure becomes 1. But what is the pressure given over here? Okay, T1 is given, and we know atmospheric pressure is around 1 atp. Okay, so we can substitute these in this equation over here. What is temperature T1? Right, I am going to substitute in this. Temperature is what? 300 Kelvin divided by T2. This is what we want to find. Okay, this value to the whole power, what gamma is 1.5. This is equal to 3.375 divided by 1 to the whole to the power of 1.5 minus 1. Very simple. Okay, 1.5 and 1.5 minus 1. What is 1.5? 1.5 minus 1. This is 0.5. How can you write 0.5? 0.5 you can write it as 1 by 2. Then what about 1.5? 1.5 you can write it as 3 by 2. Very simple. Right. So one side we have 1 by 3, one side we have 1 by 2, one side we have 3 by 2. So very simple, right? See, what we can do is we can actually eliminate the denominators here. Here 1 by 2 we can eliminate. Here also 1 by 2 we can eliminate. When this 3 goes to the other side, it will become, this will become 1 by 3, root of cube root of this value. Okay, from here what is T2? T2 is nothing but, okay, very simple, okay, T2 is nothing but this value 300 divided by cube root of this value. If you take cube root of this value, you will end up getting 1.5. Okay, so T2 over here is somewhere around 200 Kelvin. That 200 Kelvin, okay. Now 273, so you have 200 Kelvin converted into degree Celsius minus, so you want to convert means you will do minus 77, 277. So 273, right? This gives you somewhere around minus 73 degrees Celsius. This will give you somewhere around minus 73 degrees Celsius. Okay, very simple question. Okay, so what I'm going to do, I have another class now, so I'm going to end today's class with this note. So head down to the description box, okay, and actually you can, go down to the description box. There will be link given to all the special classes that's happening on the Unacademy platform every single day around the same, around 7:45 to 8:45, right? We have special classes every alternative day again for class 12 mostly, okay. So you can, class 11 actually, and you can actually enroll for those classes. Those are absolutely free classes. Okay, tomorrow again we have the thermodynamic class happening at around 7:45, okay, to 8:30 p.m. on the Unacademy platform. Alright, so do go down to the description box and you can actually register, enroll for it. It's a completely free class. Alright, so with this note, I'll see you all in the next class. And if you like the video, do share it among with your friends, subscribe to the channel, and also click on the bell icon so that before any class goes live, you will get a notification. Then I'll see you all in the next class. Bye.